Here is the homework that CA James has graded. A couple of things about the homework. This time I didn't ask TA to deduct any point um, since some of you didn't follow the guidelines that I posted on syllabus for submission of the homework. Please go back to the syllabus and read the guidelines for submission of the homework. Some of you didn't follow that instruction, so please next time follow that. It should be organized. Use the staples to put all page together. Write your name. These are some of the things that you should um, do when you submit your homework. What else? If you have any question about the grading, you can reach James. So you will have access to his contact information through the syllabus. All right. For 4-bar mechanism, we define 3 classes of class 1 when the shortest link plus the longest link is less than P plus Q. It's a Grashof mechanism. Class 2 is it's happening when S plus L is greater than 2 plus Q, non-Grashof mechanism. And class 3 is just a special case of class 1 where these two are the same. Grashof mechanism, it's suffering from change point. So these are what we covered. So for class 1, we have crank rocker. It's happening when the shortest link is adjacent to the ground. So when the shortest link is adjacent to the ground, we are going to have crank rocker mechanism. And it's for class 1. When you have Grashof mechanism, on that case, if the shortest link, which is this one, is adjacent to the ground, one link is going to be crank, which is this one, and one link is going to be rocker, which is going to be this one. Double rocker, the shortest link is opposite to the ground. So adjacent, opposite, and the last one is double crank. It's happening, the shortest link is the ground. So this is the gray shock mechanism because we know that based on the length of the links, the shortest link plus longest link is going to be less than P plus Q. The shortest link is going to be this, longest link, I guess it's going to be this one. So the summation of these two is going to be less than the other two links. And here you see the shortest link is adjacent to the ground, so we expect to have crank rocker mechanism. And as you see, it can complete the whole circle, and the other link, the output link, is gonna oscillate back and forth, which is kind of rocker. It's class 1 crank rocker mechanism. Now the same class of the mechanism, here we are going to check double rocker. So the shortest link is opposite to the ground. This one is opposite to the ground. So as you see, we are going to have two rocker, red and yellow. They oscillate back and forth, so they cannot complete 360 degree. They have been connected to the ground, so we call them rocker. We have two rocker, double rocker. And I said in the class, since it's a class 1 link should be able to complete 360 degree with respect to the other links. The blue one is that one. It's gonna complete 360 degree or the complete circle with respect to link red or link yellow. So as you see, if you just look at the yellow links, the blue one can complete 360 degree rotation about that. Or if you look at the red one, the blue one still can complete 360 rotation about that. So it's a double rocker. And we have double crank when the shortest link is the ground. Two links they are gonna complete 360 degree, red and yellow, and green one is the shortest. So we are gonna have double crank. By changing the size, you can get class 1 mechanism, class 2, or class 3. By selecting the order of the links and the links which has been connected to the ground, you can pick crank rocker, double rocker, or double crank. Alright, the other linkage that we talked about that is class 2 non-gradation. It's one of the non-gradation mechanisms that I have here. So the summation of the shortest link and the longest link is greater than summation of this length plus this one. So if this is happening, if I just start moving the input link, when it reaches to this position, these two links they line up. If you push further, it cannot go in this direction anymore. So you lock up at this position. So you should change the direction of motion for this case and moving in this direction. If you do that, then this one and this one line up, then you're stuck here. You cannot go further. You should again change the direction of motion. But as you see, there is no link which can complete 360 rotation with respect to the other. So we call it non-gradation of mechanism. Example for this one is a crank rocker, as you see. This one can complete 360 degree. The other link, which is a rocker, it's oscillate. Now, I can change the length of the links by these joints. So I'm gonna make a non-gray shock. One has a ground, 2, 3, and 4. So it's showing that when this mechanism is moving, it's gonna lock up at this position. It cannot go any further. If you push more, it cannot go anywhere. You should change the direction of motion. I did that. I mean, you can now. You are gonna be at another locking position, so you have to change the direction of motion for that. So these are some examples for this. This is another example for non-gray shock. One locking position, changing the direction of motion, you have another locking position. So this is a non-gray shock mechanism. We call it triple rocker because triple rocker or RRR. Any question so far? All right, let's look at this old feed pump, and we would like to study the mobility and gray shock condition for this one. So it's a oil field pump that you might see on the oil field. So if I draw the mechanism right here, here we are going to have the motor which is going to run the pump. So one link has been connected to the motor. It's going to run it continuously. There is one joint, another link is going to be connected to this one, and one joint is going to be up there to have this link. And there is a joint piece allowing this guy rotating about this. So if I look at this, I will see something like this. This is the ground. This is where I put the motor. This point is the ground. It's part of the ground. It has been fixed to the ground. One joint here, one joint up there, and one joint right here. So the lengths are given. This length is 14 inch. This length is 80 inch. And this one is 51.26. We are not given with this one. 1, 2, 3, 4. But we can calculate this length easily if I connect these two points. I'm looking for the distance between these two. I'm looking for this length. If I call it A and B, in this triangle, AB squared would be OB squared plus OA squared. This is 90 degrees. This squared plus this squared is going to give me AB squared. OA from this point to this point. The entire of that is 76. This is 12. If I subtract 12, I will get 76 minus 12, it's 64. So OA is 64 inch. And this length is 47.5. If you plug in here and solve for AB is gonna be 79.7, which is gonna be the ground. So ground is 79.7 inch. The other links lengths are given, and now it's a 4-bar mechanism. You can find the shortest link. Shortest link is 14. Longest link is 79.7. P and Q would be the other. P is 80. Q would be 51.26. first we are checking the ratio criteria. Shortest link plus longest link, is it gonna be less than P plus Q or greater than or equal to P plus Q? Shortest link plus 79.7. 93.7 on the left side, P plus Q would be this plus this, 131.26. So 93.7 is less than 131.26. It's a Grashof mechanism. So meaning at least one link exists to be able to complete 360-degree rotation with respect to the other link. So in class 1, which one is going to be my linkage? Say it again. Crank rocker, because we are just looking at the shortest link, and the position of the shortest link is gonna tell us which type of the mechanism we have for class 1. Shortest link is this one, it's adjacent to the ground. So crank rocker happens when shortest link is adjacent to the ground, so it's a crank rocker. One link is crank, which is this guy, which has been connected to the motor. We expected that because it should be able to complete 360-degree rotation continuously. And the rocker is going to be this one, which is going to go back and forth to do the pumping for the oil. Good? All right. So as I said, these classes are valid for 4-bar mechanism. So the ratio criteria is valid for 4-bar mechanism. So now let's talk about mechanical advantage. So I'm going to define several terms, so make sure that you don't get confused. We are going to use those terms later also. Mechanical advantage also that we discussed in this class is applicable for 4-bar mechanism. I need to define a couple of terms before we go through the mechanical advantage. If we have this mechanism, this 4-bar mechanism, 1, 2, 3, 4. So we have designed or created the mechanism to do something for us. So usually one of the links is called input link, that you put the motor or you apply the input power or motion on that, and you will get the output or desired motion on the other links. We call the first link as an input and this link as an output. So in this case, meaning that I put initial motion or the motor here, and I'm getting the desired motion from this link. I can say same thing for this slider crank. Usually you put motor here, meaning you input the motion, you expect to get the desired motion from this slider, so we call it output, this one. This link, if you remember, we defined as coupler. I'm gonna define two angles, mu and beta. Mu, the angle between output link and the coupler. So this is the output, this is the coupler. So this angle is called mu. If I change the input from this link to this one, then this angle is going to be the mu, because now this one is going to be output, this one is going to be input. Mu is called transmission angle. So again, if I change the input link from this guy to this one, then beta is going to be my transmission angle. Now, beta I define as the angle between input link and the coupler. Which is, we call it deviation angle.
What's it, is it supposed to be output
Input.
or back also?
The output is a transmission. This is transmission between output and coupler. Beta is deviation angle between input and coupler. So I'm gonna use these two angles when I define mechanical advantage. Good. Any question? All right. Suppose I have this mechanism. This mechanism is a rock crusher. So it's gonna crush the rock. You put the rock here, you put the motor here. When it's gonna move, it's gonna push this to the right side and it's gonna crush the rock. So you apply some force here, you have a motor here, you apply some force here, and through this link you apply some force to rocker. So output F in, some force coming through the input link, some force going out at the contact point between the rock and this link. So mechanical advantage is defined as output, the force that you will get at the output divided by the force that you will get you apply at the input. So F input F output divided by F input. We can prove that the mechanical advantage is going to be a constant term times sine of transmission angle divided by sine of deviation angle. So mechanical advantage is going to be constant term, which is not changing for a given mechanism, times sine of transmission angle divided by sine of deviation angle. So if I have this mechanism or this one, when the mechanism is moving, the angle of beta and mu are changing over the time. True. So at any specific time, I'm gonna have the different value for mu and beta, so I'm gonna have different value for mechanical advantage. So mechanical advantage is not a fixed or constant number for a given mechanism. It's vary while the mechanism is moving. Makes sense? Alright. If I want to get the huge force here, I need to have the high value for the mechanical advantage. How can I make the higher value, greater value here on the right side? If I get the maximum value for this one and minimum value for this one. If this is happening, then mechanical advantage is gonna be at the highest value. So what would be the maximum value for sine of mu? 1. So which angle is gonna give me the max, the 1? 90 degrees. So ideal value for a high mechanical advantage. And sine of beta, if it's 0, ideally I can get an infinite value for the mechanical advantage. It's not happening in reality, but if I want to get the higher value, the sine of beta should be close to 0, or beta should be either 0 or 180 degrees. If this is happening, if beta is a small number, sine of beta is a small number, and sine of mu is very close to the 90, I will get a huge mechanical advantage. Good? So, but as I said, the mu and beta are varying over when the mechanism is moving. The design recommendation says the range of mu should be between 45 degree and 135 degree when the mechanism is running. So this, when you want to design the mechanism, you should keep this as a rule of thumb. This slide is just explaining the mechanical advantage is going to be F out divided by F in, and it's going to show us at the end we will get mechanical advantage equals to R4, which is this guy, the length of link 4, divided by R2, length of link 2, times R in. In this case, R2 and R in would be the same. R out is going to be the distance from the distance from the contact point to the joint 4, times sine of mu divided by sine of v. I mean, I use beta. Mu is this angle, beta is this angle. So this one and this one are constant. So I label them as a constant term. So mechanical advantage is proportional to this ratio. So if for the rock crusher, if I want to have a high mechanical advantage, mu should be close to the 90 and beta should be close to the 0 or 180. The mechanical advantage is a measure of quality of force transmission. So This is why we define the mechanical advantage. So transmission angle is a factor which is changing the mechanical advantage. So if you look at this crimping tool, just look at the mechanism that we have here. We have one handle here, entire of this handle, and second handle. This goes starting from here up to point B. So this handle is gonna be one link. It has two joints, A and B. The other handle is gonna be a rigid body with two joints at A and B. And this part is gonna be another link. B. Let me draw this first. This part is gonna be link 3. And I'm gonna have so A, B, C, and D. So it's making a 4-bar mechanism for me. One link, number 2, number 3, and link number 4. The lengths are given here. AB, which is link number 2, is given 0.8. BC is given 1.23. CD, which is this guy, is 1.55. And AD is 2.4. So if I want to classify this mechanism, it's a 4-bar mechanism. Shortest link is AB, S is 0.8 or AB. Longest link is AD or 2.4. Shortest link plus longest link is going to be 3.2. Summation of other two links is 1.23 plus 1.55, 2.78. So as you see, S plus L is greater than P plus Q. So this mechanism basically is a non-ratio. So through these two handles, we apply the force. So the AB is going to be the input link, and we expected to get output force or output motion at DC. So this is going to be output, input. The angle between output and the coupler is called mu, or transmission angle, and this angle is called deviation angle, based on the definition. This angle and this angle. As you see, this angle is very close to 90 degrees, and beta is very close to 180 degrees, 175, whatever is that. It's going to give us a small number here. Sine of mu is 1. 1 divided by a small number, and you get the high value for mechanical advantage. So by pushing small amount of the force, I can get a significant amount of the force at the output. So this is how they designed the crimping tool to have a huge, the high mechanical advantage. Any question on this? This is another tool, adjustable pliers. So It has two handles. This handle is one link with two joints. This handle another link with, it's a binary link, and one link which can connect these two and this part. So it's another form of mechanism. So the output is going to be this. This is going to be the ground. So this is going to be the input. So then this angle is very close to 180. Yeah, this is the transmission angle, and not the, it's not ground, it's a coupler. Sorry. This is ground. This is
The one on top is the ground, right? It doesn't.
this is a 90 degree, so it's between output.
The input is directly connected to the output.
Say it again.
The input is directly connected to the output.
Now let me go. So this thing, yeah, that's fine. I mean, this is ground. This is beta. This is mu. Where? Yeah.
That is me. And the game. Yeah. That's what's pushing it.
The ground in that case is gonna be, because it's the output should be connected to the coupler anyway. The ground is gonna be this, not this one. It's gonna be input, so this is gonna be the ground. So then this is gonna be data mu. So this is gonna be the data, the angle that I have here, and this is gonna be the angle that I have here. So it's increasing the force, but we are not looking for the huge mechanical advantage. We got 90 degree here, which is making this one equals to 1, and we got kind of a small number here, which is going to increase the force. Alright. Let's move on next topic, which is finding the extreme value for the mu. while this mechanism is running, at different value of, if this angle is theta, the angle between input and the ground. If this is theta, at different value of the theta, mu is gonna change. So we would like to find what would be the extreme value for mu, or transmission angle, or what would be the mu max and mu min. Mu max, mu min. And we would like also find the corresponding angle to the mu max and mu min. At which input angle I will get the mu max. Corresponding input angle. Theta. Again, this is valid for 4-bar mechanism. I will start with the crank rocker. So the process that I'm going to talk about that is valid for crank rocker mechanism. Then we go to the double rocker and non-glacial mechanism. Crank rocker mechanism. So this process is valid for crank rocker mechanism. Meaning input link is crank, output link is rocker. So let me, do you remember cosine rule? If I have this triangle with the length of A, B, C, angle of theta, beta, and phi, for example, the cosine rule says if I consider angle of theta, the link opposite to the angle of theta is B. The cosine rule says B square would be equals to this summation of S squared of the other two links, A squared plus C squared, minus 2AC cosine of that angle. This is valid, and we can prove that, and it's called cosine rule. I'm going to use this. It's the reason that I'm recalling that. So you can change the angle for beta. The link opposite to the beta is C. So I can write C squared. It's opposite to beta. The other two links are A and B squared minus 2AB cosine of beta. Same things you can write for A, which is opposite to C. A squared equals to B squared plus C squared minus 2BC cosine of phi. We call it cosine rule. Question on this. We are gonna use this cosine rule many times in this course. So it's a simple one, but I needed to recall it once. All right. In this crank rocker mechanism, I will connect these two points with this dash line and label this as a M. M. So this link is A, this link is B, the length of this is C, and the ground is D. So A, B, C, and D. Now in this triangle, write the cosine rule for link M. So in this triangle, if I want to write the cosine rule for M, it's going to be M squared equals to B squared plus C squared minus 2BC. The angle which is opposite to M is mu. So again, the goal is finding the extreme value of transmission angle. What would be the maximum and minimum value of the transmission angle and the corresponding theta. So now look at this triangle with the length of A, B, and M. One more time, write the cosine rule for M. M squared would be A squared plus D squared minus 2AB. The angle of theta is opposite to M, cosine of theta. Now these two are equal to each other. The left side equals to right side. I can write D squared plus C squared minus 2BC cosine of mu equals to A squared plus T squared minus 2AB cosine of theta. So I'm solving for cosine of mu. So I move cosine of mu to the other side, moving the other terms to the left side. So it's going to be B squared plus C squared minus A squared minus T squared plus 2AB cosine of theta equals to 2BC cosine of mu. So cosine of mu, it's going to be B squared plus C squared minus A squared minus D squared plus 2AB cosine of theta divided by 2BC. A, B, C, and D are constant. The length of the mechanism they are not changing. The only thing which is varying are mu and theta. So this equation showing me how the transmission angle is varying with changing of the theta. Tomorrow I will work on this problem to find at which theta I will get maximum value for mu. Good? Alright, I will stop at this slide.